Hello everyone, welcome to the lecture for Psychology 210 covering the T-statistic. We'll talk about how amazing and wonderful the T-statistic is. A quick overview of what this lecture will cover is first, we'll talk about hypothesis testing with z-scores and what problems you might come across if you are trying to conduct a hypothesis test using z-scores. And then I'll introduce you to the T-statistic, which solves the biggest problem that you might run into with using z-scores. And then I'll go into a little bit of describing the differences between using T versus using z. In order to use T, we have to calculate something called the estimated standard error. Okay, so we've already covered what standard error is, which is the average distance you would expect between a mean of a sample and a population mean. And in this case, we're going to estimate that standard error instead of calculating it outright. Then I'll get into the shape of the T distribution, which is very similar to the shape of the Z distribution, but can change depending on the number of people that are in your sample. And I will describe what that means and how it affects your hypothesis testing in the lecture. And then I will go into how you go about conducting a hypothesis test using a T-statistic instead of a z-score. Okay? And this T-statistic is much more often used by behavioral scientists. And throughout this lecture, you'll probably figure out why. And then finally, I'll give you two ways to calculate the effect size of the difference between your mean and the population mean using the T. Okay, so for the purpose of showing you why a z-score might run into some problems during a hypothesis test, I've put together an example of something that a behavioral scientist might be interested in. So let's say that you are interested in whether American men over the age of 35 get better sleep if they exercise regularly. So if you remember back to our hypothesis testing lecture, this means that exercise is a treatment, and you as a behavioral scientist are interested in whether this treatment affects the sleep quality for men over the age of 35. So here, our population of interest is all American men over the age of 35. And like many populations that we're interested in studying, this population is just simply too large and too hard to get to study every single one in that population. So instead, we would be using a sample. And the treatment here is regular exercise. And you as a researcher would get to define regular exercise however you think is best. So remember, that would be your operational definition of regular exercise. And the dependent variable, so what you think regular exercise would affect, is sleep quality. So we'll be looking at whether men who exercise regularly get better sleep quality than men who don't exercise regularly. So let's say that you gather a sample of 25 American men over the age of 35 who exercise according to your definition regularly. And in this case, we'll say that regular exercise is at least 3 times a week. So we gather these 25 men. We put together a scale, so we might ask them, on average, how well do you sleep? Maybe we'll say 1 is horribly, I really don't get any sleep at all, to 7, I'm on a cloud of dreams all night, it's heavenly and beautiful, right? So people can rate how well their sleep is on this scale that you have created as the researcher. And let's say that on this scale, you find a sample mean of a 4.9, So a little bit above the middle of the scale, which is good. So it means people aren't getting horrible sleep and they're getting slightly okay sleep. And the standard deviation for your sample is 1.1 on the scale of 1 to 7. Okay, so now you have some data that might help you answer this question of whether American men over the age of 35 get better sleep if they exercise regularly. But if we want to use a Z-score, we need one more piece of information at the very least, right? Now what? What do we actually compare this to in the general population, right? We're missing some crucial information about the population that we need in order to conduct a hypothesis test using a Z-score. And that is your population mean and your population standard deviation. So here is where we run into trouble trying to use Z-scores in order to conduct a hypothesis test. If we're using a hypothesis test with Z-scores, we need the mean of our sample, which we do have, but we also need the mean of our population, which we don't have. And finally, we also need our standard error, which is based on the standard deviation of our population. So now we're missing two things if we want to calculate Z. We're missing the population mean as well as the standard error. Okay, so now we're kind of caught in a jam. Well, what should we do? Again, we don't know the population parameters. This is the problem. Well, we have two problems, right? We're missing the population mean and we're missing the population standard deviation, which would help us get the standard error. Now, we can start to estimate these things instead of having them calculated already. And the mean for your population is usually something that you can estimate or hypothesize with a lot of confidence and some pretty good certainty. In this case, let's say our scale is from 1 to 7 and that middle point is a 4. So we're probably thinking if most people get average sleep, right, then our mean is probably going to be close to 4. So we can be pretty confident that that's the mean we would compare our sample mean to. However, the more difficult problem is the value of that standard deviation of your population. This is much harder to estimate or hypothesize, at least with any sort of certainty. And this is where the Z-scores give you problems. But that's not to say the Z-scores aren't useful. Z-scores are very useful when you do have population parameters. And for this course, more importantly, Z-scores set up your understanding of the T-statistic, which is, again, the more popular statistical test that most behavioral scientists are going to be using. So again, we don't know the value of our standard deviation, so we can't calculate the value of our standard error, which means we can't calculate a Z-score. So we need to calculate something else. All aboard to T-Town. Now, as you'll probably learn from this lecture and a couple more lectures, I love the T-statistic. It lets you do so much in terms of figuring out whether a treatment has an effect on a group. And we're actually going to learn about many types of T-tests, but in this lecture, we'll only be covering the basic T-statistic. And then in later lectures, we'll cover what happens when you have different types of groups or different types of treatments and how you can measure the effect of those. But in general, I am a huge fan of the T-statistic. I use it all the time for my own research and think it's incredibly useful and incredibly easy to understand once you've used it a few times. So what is the T-statistic? It allows us to solve this problem when we are trying to use Z-scores, but don't have the population parameters. Specifically, the T-statistic allows us to work with an unknown standard deviation. Okay, so we cannot calculate the z-score. Instead, we're going to calculate the T-statistic because we're going to estimate that standard error. So in order to compute the T-statistic, we're going to use the variance from our sample to estimate the standard error of the treated population. So let's put this in terms of the example I just gave you. I'm interested in whether men over the age of 35 get better sleep if they exercise regularly. And I had a sample of 25 and got some statistics for them, their mean and standard deviation, but I don't have the population mean or the population standard deviation in order to calculate my standard error. And remember that that group of 25 men that I brought together and found the mean for is really meant to represent all of the men who exercise regularly that I'm interested in, right? So they represent the entire treated population. And so that's why I say I'm trying to estimate the standard error of that population, the population of men that exercises regularly. Okay, so that is what I'm trying to estimate in the T-statistic because I don't have it. Okay, so we're going to introduce this new statistical notation. It's SM, or our estimated standard error. Okay, so and it's not, I don't like the T-statistic just because it happens to have my initials, but that probably doesn't hurt. Okay, so this is what we're going to call our estimated standard error. Okay, and we are going to calculate it this way. So we will take our variance, which is represented here with this S squared, the variance of our sample, and divide it by the size of our sample, here represented with n, and then take the square root of that resulting number. Okay, so that is how we're going to estimate our standard error so that we can still run a hypothesis test even though we don't know the parameters of our population. So once we have our standard error, we can then go ahead and calculate our T-statistic. And this should look pretty familiar. So we're going to take the mean that we got from our sample. So in this case, our mean would be 4.9, if you remember from a couple of slides ago. And we're going to subtract our population mean. And now you might be thinking, but you just said we don't have our population parameters. And you're very right. We don't have our population parameters. So for that, we're going to give our best educated guess, right? And so like I said, if we give people a scale of 1 to 7, that 4 is smack dab in the middle, and if we think that on average people should get an average quality of sleep, then we can estimate or give a really good educated guess that our mean would be 4. Okay? And then we're going to divide that resulting number by our standard error, which we figured out over here. Okay? So this looks a lot like our z-score formula, right? The only thing that's changed is that we're not using standard error, we're using estimated standard error. And we have a way to figure that out that's also somewhat similar to our standard error formula. Okay, so the way that we run a hypothesis test when using a T-statistic still uses the basic steps, right? So we figure out what our null hypothesis is, we check for our critical region, we see if our T-statistic is in that critical region, and then we either reject the null hypothesis or fail to reject. All of that stays the same. The only thing that's different now is the test that we're using. And really, as we go forward in the course, that's the only thing that's going to change. The hypothesis testing is what we want you to walk away with knowing. Okay? Not only does that help you conduct research, which I think is awesome and fun and amazing, but it also helps you understand research really well. When you're reading it, when it's in the news, when your professor talks about some study and talks about the T-statistic, you're like, I know what that is. And so the hypothesis testing is what we want you to know. And now we're going to introduce you to many different tests that can help you with the hypothesis testing that you're trying to conduct. So in this case, we're talking about the T, which, like I said, is one of my favorite tests. So let's keep talking about it since it's my favorite. So as we just went over, it uses estimated standard error instead of actual standard error because we don't have our population standard deviation. And that is the formula I just showed you, okay? So we're just showing you again, getting you used to it. You know what you're working with. And you'll notice that we're using our population variance. And when we first started working with variability, our variance was really sort of just a stepping stone, just one calculation away from our standard deviation. And many students always are like, why do you want to know this variance? Why do you always ask about it? And this is why, because at some point later on, it will become important, right? And so now we're using variance, and make sure that as you're calculating, you're not using standard deviation, you're using your variance. So please notice that it uses your sample variance within the formula. And if you remember, variance is simply your sum of squares. Oh, don't you miss your sum of squares. Your sum of squares divided by your n minus 1, right? And so n minus 1 we said we use because we want to account for the error that we get within a sample from the population. So this helps us get a variance that is more true to what the population variance is. And that n minus 1 is now going to become important. This is an important concept. So n minus 1, as you may remember from reading about it when you were first introduced to it or from class, this is degrees of freedom. And we're going to note that with DF. Okay, this is going to now become an important part of the T-statistic. So n minus 1 is our degrees of freedom. And just a short definition of what that means is that it's the number of scores in a sample that are free to vary. Now, what does that mean? That means, let's say I have a sample of 5 scores, and I know that their mean is 34. Okay, so I have a sample of 5 scores, and I know that their mean is 34. Those first 4 scores can really be whatever. They can literally be almost any number, right? Except that once you get to that 5th number, it will be defined by those other 4 numbers. Okay, so once you get to that 5th number, it must be whatever will turn the mean into 34. Okay, so you can have any set of numbers for those first 4. Those are free to vary, but that 5th one must lock into place so that my mean is still 34. So that's what we mean by degrees of freedom. Now, you'll notice that your sample size is here for your standard error, very similar to what it was for our regular standard error, right? And now we're also taking degrees of freedom into consideration for our estimated standard error and our T-statistic. Okay, so your sample size is greatly going to affect the T-statistic that you need to fall into the critical region. And this will become more clear once I show you the table that you'll be working with. So what we're basing all of this on is what we call the T distribution. And this will look familiar to you because it looks pretty similar to your Z distribution. So remember, our Z distribution had a mean of 1 and a mean of 0 and a standard deviation of 1, which is what I meant to say. So a mean of 0 and a standard deviation of 1, right? And because of its normal shape and the mean of 0 and the standard deviation of 1, we could use it to define the probability of a certain mean, right? Because we know how much of the population will fall in any given region. So the t-distribution is going to work very similarly, but now the distribution actually changes a little bit depending on your sample size. So let me show you what it looks like. So your mean is still 0. The curve itself is still symmetrical. So remember, if you fold it along that mean line, the two sides will look exactly like one another. However, the actual variability, right, or how narrow or flat it is, actually depends on your degrees of freedom, which, as we now know, depends on your sample size. So you'll notice that the shortest, sort of widest distribution, which is that solid line, is what it looks like when you have only 5 degrees of freedom. Okay? And as your degrees of freedom become more and more, that distribution will look more and more narrow. Okay? So this middle line, the one that has sort of the longer dashes, is what the distribution looks like if you have 20 degrees of freedom or a sample size of 21. So what you'll notice is that the amount that now is in your critical region changes depending on how many degrees of freedom you have, and clearly that will affect whether or not you can reject your null. And this very top distribution, the one with the smallest dashed lines, is actually the Z distribution. It's a normal distribution. So you can see that the T actually looks a lot like it. And as your degrees of freedom goes higher and higher, it will actually look more and more like your Z distribution. And at a certain point, basically be the same as the Z distribution. Okay, so the T distribution is basically taking into account that we're using a lot of estimating, and our estimations get better and better as our sample gets bigger and bigger, right? So as our sample gets bigger and bigger, our degrees of freedom gets bigger and bigger, and our distribution looks more and more like our Z distribution. Okay, so you don't have to worry too much about trying to find the critical region on an actual distribution. Just like you did with the Z distribution, you will be using a table. So this time it won't be a unit normal table, it will be a specific table just for the T-statistic. So like I said, this is very similar to your Z distribution, but different. It tends to be a little bit shorter and a little bit wider. All right. There's more variance, again, because we're estimating our standard error instead of calculating it. Okay, so whenever we estimate, we try and, be cautious with our estimations. So we want to make sure that we are accounting for sampling error and things like that, and so our variance will go up. Not only that, but the distribution is going to change depending on your degrees of freedom, okay? And this becomes important. You'll have to know your degrees of freedom because this will actually be a part of looking up your critical T on the table. So again, the higher the degrees of freedom, the closer it is to the normal Z distribution, okay? So at some point, it basically becomes the normal Z distribution. So when you want to see, once you've calculated your T statistic for your particular sample, you need to check to see if it's significant. Okay, and so you use the T-distribution table, and I'll show you what that looks like in just 1 second. So your entire job is to find whether your T value or your T statistic surpasses your critical T. Okay, so I should say surpasses your critical T. So let me quickly show you what the table looks like. So this is in the back of your book, and it's table B2, and this is the T distribution. Now it gives you a little image. Just like with z-scores, you can hypothesize either a direction of change, so you can hypothesize an increase or a decrease in your dependent variable, which would lead you to conduct a one-tailed test. Or you can say, I'm not quite sure whether the direction is known yet. So I'm going to say it just causes a change. And either it's going to increase it or it's going to decrease it. And in that case, you would be conducting a two-tailed test. Okay, and so this is just reminding you of what a one-tail or a two-tail test looks like on the distribution. But in order to save you a little bit of room and time, the table has combined the alpha levels for you. So if you are hypothesizing a direction, right, you're conducting a one-tailed test, so you're looking at this row right here where it says proportion in one tail. Okay, and you're really never going to go further to the left than this column here, right? So this would mean an alpha of 0.05 if that is what you're testing against. This would be an alpha of 0.025, an alpha of 0.01, and an alpha of 0.005. Most behavioral researchers are working with either an alpha of 0.05 or an alpha of 0.01. Okay, so you're either going to be looking in this column or in this column. So again, if you're only thinking that the effect is going to either increase or decrease the dependent variable, so let's say I'm looking for an increase in sleep quality, right? So I am hypothesizing a direction. Then I'm looking at this top column or this top row here. And if I say I'm setting my alpha level at 0.05, and now you'll notice that there's this entire column of numbers, right? And so I have to figure out which one of those is my critical T. And the way that we're going to figure that out is simply by looking over to the left and finding our degrees of freedom. Now, if you remember from the first example I gave you about sleep quality, we had a sample of 25 men. And your degrees of freedom are simply n minus 1. So in this case, our degrees of freedom is 24. So we have 24 degrees of freedom. We're simply going to look to the right until we get to our alpha of 0.05. And now we see that if we want to reject our null hypothesis and find support for our alternative hypothesis, then we need a T statistic that's at least 1.711. All right, so that's how this table works. First, you'll need to decide whether you're conducting a one-tail or two-tail test. Then you'll need to decide your alpha level. And finally, you look up your degrees of freedom. And you'll notice where the degrees of freedom, it goes one by one until it gets to 30, and then to 40, and then to 60, and then to 120. If you have more than 120, you go down here. And that's when it basically starts looking like your Z distribution. And you'll notice, right, that in our one-tailed test with an alpha of 0.05, we have 1.645, which is very similar to the Z score that would be at that alpha level. Now, if you are conducting a two-tailed test, so maybe I say, I don't know, exercise could go either way. Maybe regular exercise leads to better sleep quality because, it's good for your health and things like that. But maybe regular exercise also, increases your heart rate and so you can't sleep as well at night, etc., etc. So maybe I don't actually know whether it's going to increase or decrease sleep quality. So my alternative hypothesis is going to be simply that men over the age of 35 who exercise regularly have different sleep quality than men who don't exercise regularly, right? So again, I don't know if it's going to increase or decrease, so I'm just going to run a two-tailed test. In that case, I look at this second row. Okay, so now I'm in the second row. That's the first thing I have to figure out. What kind of test am I running? One-tailed or two-tailed? In this case, we're going to say two-tailed. Okay, and then you have to, what's the next thing? Decide your alpha level. Okay, so you're never going to go to 0.5 or 0.2 or 0.1. That's silly. So here we have an alpha level of 0.05, an alpha level of 0.02, and an alpha level of 0.01. Okay, so let's keep it the same. We're going to use an alpha level of 0.05, right? So we have the two tails, an alpha level of 0.05, and we already remember our degrees of freedom from the last time we did this. And let's see, that gives me now a T-statistic, a critical T of 2.064. So now it's going to be a little bit more extreme before I can reject my null hypothesis. And that makes sense because we're splitting that alpha of 0.05 between those two tails, right? Between those two tails. So now it's 2.5% on the right and 2.5% on the left, which does mean that my T must get more extreme before I can reject my null. And you'll notice that as your degrees of freedom gets larger, that critical T actually gets smaller. Okay? So this, again, the benefits of a larger sample size, right? Your critical T gets smaller, so you don't have to find as extreme of a T statistic in order to reject your null. All right, so that's how you use the table. One more time, you decide whether you're going to run a one-tailed or a two-tailed test. That will tell you whether you're looking at this first row for the proportion in one tail, the second row for the proportion in two tails. Once you do that, you decide your alpha level, usually either 0.05 or 0.01. Once you decide your alpha level, you go down that column until you reach the degrees of freedom for your sample, right? So that's how we're going to use the T-statistic table. Very different from our Z-score table. This is actually only on one page. So much shorter than our Z distribution and our unit normal table. So let's go back to learning about that wonderful T. Let's just quickly go over how you would conduct a hypothesis test with a T-statistic instead of a Z-score. So as always, you begin with your hypotheses, right? We have two hypotheses that we need to state. One is our null hypothesis, right? That little zero means zero difference. We're expecting no difference in the null hypothesis, right? So in this case, I would say men over the age of 35 don't experience any difference in sleep quality, even if they exercise regularly. And then we have at least one alternative hypothesis, but we can always have more depending on the study that we're running. In this case, my alternative hypothesis would be men over the age of 35 get better sleep quality if they exercise regularly than if they don't. Decide if you are going to use a one-tailed or two-tailed test. I, in this example, decided to hypothesize an increase in my alternative hypotheses, an increase in sleep quality. So I would be running a one-tailed test. You set your alpha, which again is your proportion in the tail. I'm going to go with the tried and true alpha of 0.05. find your t-value, right? So I would use my mean and standard deviation that I found early on in this lecture. And then I check it to see whether it's in the critical region. So does it surpass that number that I found in the tail? And I apologize for that quick typo. Just check if it is in the critical region. And of course, once you do that, you can either party or be sad. So in this case, we're looking at an alpha of 0.1, which I would never use, but I just want to show you what it looks like. Then you decide what to do with your null. So remember that when you're conducting a hypothesis test, you're always testing against that null. You want to think about your null like an arch nemesis, right? You don't even really care too much about your alternative. It's that null hypothesis. You want to take down that null hypothesis. So you either reject, happy day, or you fail to reject your null hypothesis. Okay, so remember, everything is in terms of that null, right? So either you reject it, you reject your arch nemesis of the null hypothesis, or you fail to reject that arch nemesis of your null hypothesis. And if you do reject it, you find support for your alternative. Remember, we can't prove anything using hypothesis testing. Instead, we can find support for. So if it's true that my T-statistic is in that critical region, I would say I reject the null hypothesis, that there's no difference, and I find support for my alternative hypothesis that regular exercise increases sleep quality. Okay? Because remember, someone can come along and say, well, 3 times a week helps sleep quality, but if you have someone say 6 times a week, that doesn't help sleep quality, right? So someone else can come along and find support for a slightly different hypothesis than mine. So that's why we can't prove stuff, but we can find support for our hypotheses. Moving right along. So let's look at this example. Do American men over the age of 35 get sleep if they exercise regularly? We have a sample of 25 men over the age of 35, and they exercise regularly according to our operational definition, which is at least 3 times a week. We ask all 25 men, how well do you sleep? They rate their sleep on a scale of 1 to 7. Their mean is a 4.9. In this case, I'm giving you your sum of squares, which is a 26.4. So if you remember, we had a reasonable estimate of our population mean. And this has to do with our scale here. We have a scale of 1, 2, 3, 4, 5, 6, 7. Okay, so that means 1 through 3 is not very good sleep, right? 1 is horrible, don't really get to sleep, I toss and turn. 2 is, yeah, I get a little bit of sleep, but it's not great. 3 is, it's all right, but it could be better. 4 is, it's okay. 5 is, it's all right, it's pretty good. 6 is, it's amazing, I love it. And 7 is, I feel like I'm on cloud of dreams, right? So 1 through 3 are really bad sleep, and 5 through 7 are good sleep. And 4 is just, yeah, it's all right, right? And so we're going to use that. We're going to use that as our reasonable estimate of our population mean. So in our practice, I want you to use these numbers to figure out whether or not I have support for my alternative hypothesis. So make sure to write down these numbers, and we will head over to practice and go through this for the first problem. Now let's talk quickly about that p-value. And remember, our p-value is going to relay whether your t-value or your t-statistic is significant. Okay, so when I report my mean differences, I say, you know, my group of men that I recruited had a mean of 4.9 on a scale of 1 to 7. This was significantly, different with a p-value of 0.05. Okay, so that p-value is so important. It is what we live for as behavioral scientists. When we get a p-value that's just bigger than the one that we were testing with, it is a sad day. If you come across a behavioral scientist who is testing with an alpha of a 0.05 and got a p-value of a 0.06, you should really just pat them on the shoulder and tell them it's going to be okay, because it's a rough day. All right. So the reason we have the notation of p, right? So you're like, why don't you just use alpha? If you're setting your alpha, just use alpha. Because p is the statistical notation that's saying it's the probability of getting your sample mean due to error. Okay, so when I say I got this mean and my p-value was less than 0.05, what I'm saying is the probability that my sample mean that I got from these 25 men being just due to chance, just due to error, I just happened to pick 25 men who get pretty good sleep, that chance is less than 5%. There's a greater than 95% chance that the reason they get better sleep is because they exercise regularly. Okay, so we want the probability to be low. Okay, so the P is the probability of getting our mean just due to chance or error. We don't want that. We want that number to be low, right? So if your t-value or t-statistic is significant, we reject that null hypothesis. Woohoo! Party time, right? And so you're going to report that it's significant as either your p, or the probability of getting your sample mean due to error, is less than 0.05 or less than 0.01. And I know some students get a little bit confused with these carets. Right? It's like, which one goes to which side, right? So the smaller side means less than. So P less than 0.05, right? So P less than 0.05. The mouth goes to the bigger side, all right? So 0.01 is more than my p-value. Yeah, woohoo, right? Or 0.05 is bigger than my p-value, all right? So the little point is the smaller side, the mouth is the bigger side, okay? So you want a probability to be low of getting your mean just because of error. If your t-statistic is not significant and we've failed to reject the null, now this is no bueno. We have a p bigger than, right, because it's the mouth, p bigger than 0.05, or p bigger than 0.01. So remember, this depends on your alpha, which you decide before you even run the test. So if you are like, oh, I'm going to run a 0.01 because I want to be really sure that this is an effect, and you don't get it, and then you say, maybe I should check it with a 0.05 and see if that's significant. That's not very ethical. That is not being a good behavioral scientist. So you're going to say, nope, didn't get it, didn't get it. Most of the time we're looking for this 0.05, okay? Below that 0.05. This, to a psychologist, to a psychological researcher, this is money. Money! Right here, okay? This is sad day. Sad day. In fact, I think I have a little sad face. This is not good, okay? So we're looking for a P of less than 0.05. That's a happy day. That is a happy day. Okay, so let's go on to effect size. So let's say that you get a significant t-statistic. Party time! You've rejected your null. You found support for your alternative. And now you want to say, well, okay, I know that I have a significant difference, but I'd kind of like to know, how big is my effect, right? Is it something that's, kind of just a little bit, or is it something that's really drastic, All right, so we're going to use Cohen's d to figure that out, as well as one more measure of effect size, which I will introduce you to. So remember, that before, when we calculated Cohen's d using z-scores, we simply took the mean from our sample, subtracted the mean from our population, and divided by the standard deviation of our population. So remember that Cohen's d is the difference in units of standard deviation. But just like before, we run into a problem. We don't have the standard deviation of our population, so we're going to have to use the standard deviation of our sample. All right, so when we're using a T-statistic, we're actually using the standard deviation of our sample. But because we're using this standard deviation instead of the one for our population, we're now going to call this, there we go, we're now going to call this estimated Cohen's d. So we have to be truthful and say we're estimating this based on our sample and not using our population. Our population mean we can still estimate, right? So we did that with the T-statistic. We can still estimate. So if we say, oh, our scale is 1 to 7, we expect most people will be around the middle, which is a 4, right? We can do that. Okay, so our effect size is in units of sample standard deviations. Okay, so just like we did Cohen's d before, units of standard deviation. So when you figure out Cohen's d, it tells you something about how your independent variable affects your dependent variable. So remember, in this case, our independent variable, or our treatment, is exercise, and our dependent variable is sleep quality. And so if our d is 0.75, then we can say that on average, our independent variable changes the dependent variable by 0.75 standard deviations. Now, this sounds a little dry and a little boring, and it kind of is, but you have to remember that this is just sort of the template. You're going to fill it in with whatever research study you're conducting, right? So in this case, our independent variable would be exercise, our dependent variable would be sleep quality, and our standard deviation would be whatever we figured it out to be, right? And so we could say, oh wow, according to our study, right, exercise will affect sleep quality by this much. So this is where the news stories get those headlines, right? So you could see, if you run this study and you say, exercising 3 times a week can improve your sleep quality by 50%, right? That sounds like a headline that you might read in a newspaper or on, I don't know, BuzzFeed, or see on the news, right? And so that effect size is where they get that. Okay, and so as you can remember from the last time we talked about Cohen's d, the magnitude of d can also be evaluated just depending on the actual size of it. So if we have a Cohen's d that is about 0.20, we're going to call that a small effect. If we have Cohen's d that's around 0.5, that's a medium effect. Truth be told, most research studies have a Cohen's d that's somewhere between small and medium. To get anything larger is very rare, okay? There's just a lot going on. People are complex. Context is crazy. Lots of stuff is happening. So to get a really huge change is just very rare. When you get it, that's awesome and amazing. But if you only get, quote unquote, only get a small or a medium effect, that's actually pretty normal. If you do happen to get a Cohen's d of 0.80, we're going to call that a large effect. And if you get something over 0.80, that's a very large effect, and you might be in the running for some sort of behavioral scientist prize. So if you get something over 0.8, then that's a really good day. All right, so that is estimated Cohen's d using our T-statistic, and now I'm going to go into a new way to calculate effect size for the T-statistic, and that is what we call R squared. And R squared is a different way to calculate your effect size, and it's not in units of standard deviation. Okay, so that is the biggest difference between Cohen's d and R squared. And whether you use Cohen's d or R squared is really up to the researcher. People tend to have a preference for one or the other. Sometimes journals will ask for one or the other, so they might not want Cohen's d, they might want R squared, or they might not want R squared, they might want Cohen's d. So it's useful to know how to use both, and often one will make more sense than the other to researchers. So instead of being in units of standard deviation, we're going to look at the variability. Okay, so what we're doing with R squared is calculating the proportion of variability in the dependent variable explained by the independent variable. Okay, sounds a little dry, I know, but remember, it's a template. So clearly, my mean for my 25 men who exercise regularly is different than the mean I would expect, right? That expected mean. So 4.9 is different than 4.0. That much I know. And there's also variability, right? There's variability in your sample, and there's variability in your population that you are estimating. So that variability in sleep quality is what I'm interested in. How much of that variability in my sleep quality, so some men are sleeping great, some men aren't sleeping so great, right? How much is that due to the exercise? That's what R squared is telling me. So we might not look at exercise, we might look at meditation. These are actually two of my favorite things. You should all be exercising regularly and meditating. I am a strong advocate. So in this example, R squared can explain how much of the differences in sleep quality are due to meditation and not, say, confounds, which you might remember from very early on in the class, sampling error. I just happened to get people who were really good sleepers, random noise, right? Maybe some people are really stressed out right now, so they're not getting as good sleep, or some people just finished a big project, so they're getting great sleep. All of that stuff can explain why my sample has the variance that it does. But what R squared is going to tell me is how much of that variance is actually just due to that exercise. And so that's pretty powerful. So the way that we're going to calculate R squared is simply by taking our T-statistic, we're going to square that bad boy, and then divide it by T squared plus your degrees of freedom. Okay, so you simply calculate R squared using this formula here. And just like Cohen's d, we have different numbers that we can evaluate as different levels of magnitude depending on their size. And you'll see that these numbers are very different from Cohen's d. So if we have an R squared of 0.01, which seems so small, I know, we have a small effect. Again, this is when you find a significant effect, you can say, well, it's significant, so meditation is clearly affecting sleep quality, but it's just not affecting it by very much, right? So that's what you would say if you get an R squared this small. If you have a 0.09, now you can start saying you have a medium effect. Oh, well, okay, it explains a good amount, fair amount of the sleep quality. If you have an R squared of 0.25, you actually have a large effect. So you can explain a whole bunch of the variance in your sample due to the treatment. In this case, either exercise or meditation, depending on which one you're thinking about. And finally, if you have an R squared of over 0.50, you have a very large effect, right? So these numbers look very different from Cohen's d, but again, we're looking at how much of your variance in your sample is due to the treatment, due to the independent variable that you introduced because you were interested in it, right? So again, effect size is where the headlines come from, right? So you might say, oh, one of the biggest contributing factors to sleep quality is how much you exercise. That headline would come out of knowing your R squared. That's where that headline comes from, right? Because without your effect size, all you know, the headline simply reads, exercise affects sleep quality. That is not that exciting. But when I can say exercise is one of the biggest contributors to sleep quality, that's a catchy headline. So effect sizes are where those headlines come from. Okay, so that is all I have for your T-statistic. I hope everyone is with me on the train to T-Town. And we will go over some practice in the next lecture. Thanks, everybody.